Hello students, welcome to the fourth part of our fifth module. So in the previous sessions we have studied the various relationships, Rayleigh relationships for a perfect gas. Rayleigh relations for a perfect gas were discussed in the previous session. Today we are going to learn the amount of heat transfer, the derivation for amount of heat transfer. So basically Rayleigh flow is a flow in which there is heat transfer either from surrounding to the fluid or fluid to the surrounding. So we will try to get an expression for the amount of heat transfer. So students, we know the steady state energy equation, steady flow energy equation, SFE, steady flow energy equation. So this is one of the governing equations that will be used for derivation. If you consider a particular duct and a control volume like this, let this section be 1, this section be 1 and the second section be 2 of the control volume. Okay, so there will be a heat transfer Q. If this is the static enthalpy here is H1, static enthalpy here is H2, velocity here is V1, velocity here is V2. Okay, temperature T1, here T2. Assume that there is no heat work transfer, because in a Rayleigh flow there won't be any work transfer. Therefore, W is equal to 0 and no mass addition. No mass addition. Okay, so mass flow rate remains constant, that is m dot will be a constant, and there is no elevation change. There is no elevation change. Elevation change means the inlet and outlet, the entry and exit are at same level, that is Z is a constant. Z1 is equal to Z2. Okay, so we can write the SFE equation like Q plus H1 plus V1 square by 2 will be equal to H2 plus V2 square by 2. This is the equation for steady flow energy equation. So you can rearrange this equation as Q is equal to some H2 minus H1 plus V2 square by 2 minus V1 square by 2, right? So students, you know that H0 is nothing but H1 plus V1 square by 2. H01 is equal to H1 plus V1 square by 2. H02 equal to H2 plus V2 square by 2, right? This is stagnation enthalpy, static enthalpy plus this kinetic energy term. Okay, so students, have a look at this. Here you can see that H2 plus V2 square by 2 is there, minus H1 minus V1 square by 2 is there. So you can write Q as H02 minus H01, right? So heat added will be the difference in the stagnation enthalpy of the corresponding sections, right? Okay, so we know that H is equal to Cp into T, therefore H0 will be Cp0 into stagnation temperature, right? So I am substituting, I am converting these equations of Q as Cp into T02 minus T01. Actually it was H02 minus H01, and I converted this equation as Q equal to Cp into T02 minus T01. So Q equal to Cp into T01 is taken as common and it will become T01 minus 1, right? So I am taking Cp to the left hand side. So it will become T01 into T02 by T01 minus 1. Okay. Now I am dividing both sides by static enthalpy at section 1 T1, dividing by T1. So in LHS, if dividing LHS, you have to divide in RHS also. So T1 T02 by T01 minus 1. Okay. Students, now you have this relation, this ratio, stagnation temperature by static temperature and stagnation temperature ratio. These two ratios you have with you. So this is Rayleigh relation, this is Eisenhower, T01 by T1. Basically, you know, Q by Cp T1 is nothing but T01. T01 by T1 is 1 plus gamma minus 1 by 2 m1 square, right? Okay, and now T02 by T01. That relation you have studied in the previous session. Hope you remember that relation. It is like 1 plus gamma m1 square by 1 plus gamma m2 square, okay, into 1 plus gamma minus 1 by 2 m2 square by 1 plus gamma minus 1 by 2 m1 square into m2 square by m1 square. So this is the equation for T02 by T01, and what remains is 1 minus 1 is remaining. This is the relationship. This is the relation for Q by Cp_T1. Actually, why I have divided T1 here? Because Cp_T1 will be a heat, amount of heat, right? So heat by heat will be a non-dimensionalized form. So in order to make it a non-dimensionalized form, I have divided by T1. So Qp by Cp T1 will be a function of Qp by Cp T1 will be a function of now what? M1, M2 and gamma. M1, M2 and gamma. Purely a function of M1, M2 and gamma. So if you know the Mach number at the inlet and if you know the Mach at the outlet and gamma of the flow, you can get the Q by Cp T1. Okay. So now you have already studied that if this is the Rayleigh line in HS diagram. Okay. Where is the point? You know the term thermal choking, right? Thermal choking is the point at which what? So this is H and this is, sorry, somewhat like this. So this point will be H and this point will be S. So this is the point at which maximum enthalpy becomes maximum, right? And you can add heat up to this point, right? So maximum possible heat addition will be, so here Mach number is equal to 1, this point. You can add heat up to the point where up to the point where entropy becomes maximum. So you can add heat. If it is subsonic, you can heat. If your starting point is here 1, you can add heat up to this point. If your starting point is 2 in the lower branch, that is supersonic branch, still you can add heat up to this point only. So you can add heat up to the point of maximum entropy, right? Maximum entropy. So the second Mach number M2, this equation here, this equation will become Qmax if M2 equal to 1. Okay, so substitute M2 equal to 1 here. M2 equal to 1. So Qmax by Cp T1 will be 1 plus gamma minus 1 by 2 m1 square and 1 plus gamma m1 square by 1 plus gamma only because m2 is 1, and this can be rewritten like 1 plus gamma plus 1 by 2 by 1 plus gamma minus 1 by 2 m1 square into 1 m2 by m2 square by m1 square, that will be 1 by m1 square minus 1. So this is the equation. So you can rearrange this equation like, you take this 2 to here, so it will become 2 plus gamma minus 1 by 2 whole divided by 2 m1 square into again 1 plus gamma m1 square by 1 plus gamma. So this will be, so here a whole square is there, right? Okay, a whole square is there, don't forget to write that whole square. Actually here a whole square is there, so just forgot to write that. And 1 plus gamma whole square into, if you simplify that, gamma plus 1 by 2 plus gamma minus 1 m1 square into 1 by m1 square minus 1. Okay, so if you continue to simplify this, you will get a final answer like 1 minus m1 square whole square by 2 into 1 plus gamma m1 square. Okay, so try to simplify this on your own. I have skipped a lot of intermediate steps. Okay, so don't worry about steps, those are very easy, but you should be able to write the final answer. Okay, final answer. So Qmax by Cpt1 is equal to 1 minus m1 square whole square by 2 1 plus gamma m1 square. So now Qmax is now a function of Cpt1 is a function of only m1 and gamma. So m2 is 1. So it is only a function of m1 and gamma. So now we can do a problem based on Rayleigh flow. So here it is given that air at a Mach number 1.5. So we have a duct here. Okay, so air at a Mach number 1.5, pressure 300 kilonewton per meter square, temperature 288 Kelvin, is brought to sonic velocity in a frictionless constant area duct through which, so here Mach number first section m1 equal to 1.5, given static pressure 300 kilonewton per meter square and static temperature 288 Kelvin, and since this is a constant area duct which is frictionless, so this flow will be it will be definitely Rayleigh flow. And the question says that in the second section m2 is 1 because it is at the sonic velocity, so m2 is 1, and we have to calculate final pressure P2, T2 and total heat added Q. Okay, so students, we have to take the table for Rayleigh flow with the gamma equal to 1.4. Since flowing fluid is air, you can take gamma equal to 1.4. Okay, given m1 equal to 1.5, p1 equal to 300 kilonewton per meter square, T1 equal to 288 Kelvin, and m2 equal to M2 equal to 1, M2 equal to 1, or V2 equal to A2, so on equal to. So from gas table corresponding to M1 equal to 1.5, you will get T1 by T01 at M is equal to T1 by T by T0 corresponding to Mach 1.5. So from where this you will get this is stagnation temperature ratio. Stagnation temperature ratio you will get from isentropic table. So this is stagnation, always you get stagnation temperature ratio from isentropic table only. Okay. So it is around 0.6896. You won't get that particular ratio from here, because here it is for Rayleigh flow. Stagnation ratio is obtained from isentropic tables only. Okay. So you will get 0.6896. Okay. So T1 by T01 is equal to 0.6896, and T1 will be okay. Now T01 will be T1 by 0.6896, and it is 288 by 0.6896, and this value will be 418 Kelvin. Okay, 418 Kelvin. Why I have calculated T01? Because Q is nothing but Cp into T02 minus T01. So you need to find T01 and also T02. Now we have found T01. You don't know the correct values corresponding to T02. Okay. So you have to calculate now P2 by P1 by P2 can be written like, since M2 is equal to 1, P2 can be written as P star, because M2 is 1 means it is a critical state. So P2 can be written as P star. So P1 by P star is nothing but P by P star corresponding to Mach equal to 1.5, and that value you can obtain from this particular table. You can see that P by P star corresponding to 1.5, it will be 0.578. Okay, 0.578. So P star will be P by 0.578, P1 star will be P star will be P1 by 0.578, and it is 300 kilonewton per meter square by 0.578, and it will be 519.03 kilonewton per meter square. So this is P2 is equal to P star equal to 590. So that thing you have obtained. Now you can move to T2 should be found. T2 is equal to T star only, because second section is critical section. So T1 by T2 is equal to T1 by T star is equal to T by T star corresponding to Mach 1.5. Similarly, you obtain same value for T by T star. You can see T by T star corresponding to 1.5 will be 0.75. It will be 0.753, right? 753. So T star will be T1 by T2 is equal to T star equal to T1 by 0.753. T1 is already given in the question as 4, how much? 288, right? 288 by 0.753. It will be equal to 382.47 Kelvin. Now you got T2. Now T02 should be found out. T02 is nothing but T2 by T02 here you have a particular table where you can get the value for T0 by T0 star. T0 by T0 star. What is T0 here? T0, that is T01 by T02 is nothing but T01 by T0 star, because T02 is same as T0 star. And it will be T0 by T0 star corresponding to MAC equal to 1.5. MAC equal to 1.5. And that value you can obtain from corresponding to T0 1.5, T0 by T0 star is 0.909, right? 0.909. 0.909, and T0 star will be equal to T0 1 by 0.909. T01 is already calculated as 418. You have already calculated T01 480 Kelvin. Okay, so take that 480 Kelvin here by 0.909 is equal to 459.84 Kelvin. So Q will be Cp into T02 minus T01, that is Cp of air is 1.005. It won't be given in the question. You have to remember that value, 459.84 minus 480, and it will be around 42 kilojoule per kilogram. Why kilojoule? Because 1.005 is kilojoule per kilogram Kelvin, right? So that is why the value is here, it is kilojoule per kilogram. So this is how a problem is solved in the case of Rayleigh form. So this is a very simple problem, a direct problem. So in the next session we will do somewhat difficult problems, 2-3 difficult problems, and we will wind up this module. Okay. So next module is a simple module, it is more of a theory topic. It consists more of theory topics. No more problems will be there in the 6th module, and we will wind up this module in the next session. For the time being, I am stopping this session. Thank you.